Today I'm excited to introduce to you one of the new features of the Autochem 3 vapor generator and show you some of the applications of it in a few case studies for water sorption. For those who are familiar with our vapor generator and legacy products, the vapor generator is capable of handling a long list of vapors. And in general, with the usage of corrosive probes, we do offer more protection with corrosion-resistant models. The vapor generator is easy to use and it allows the introduction of vapor as pulses and now also able to be introduced as a continuous flow. This offers more speed for studies that only needs to saturate the material for TBD quickly, and it also adds versatility in studies that need quantifications of large amounts of vapors or to keep the sample under a specific vapor pressure. There are multiple temperature-controlled zones that give the generator added performance and repeatability. We will go over the functions of these zones. Lastly, the software is embedded with simple calibration sequences that are automated by the instrument, allowing simple and easy translation of raw signal for quantification. So for today's discussion, we will talk first regarding how vapor is generated in the vapor generator. The vapor pathways via pulse versus continuous flow. We will show examples of the automated calibrations performed from both pathways. Next, we introduce a test case using calcium oxalate monohydrate with a temperature program desorption test. We will compare the water desorbed to values reported by the continuous flow and by pulse calibrations mentioned previously. The last case study is looking at the adsorption and desorption data using the TCD with a ZSM5 zeolite material, and we will vary the silica to alumina ratios. We will also compare it to a static and gravimetric isotherm collected with different instrumentations. The vapor source for the generator can easily be removed to change or replace vapors. The threaded glass makes reattachment quick and can be filled up to 50 milliliters, which typically lasts for weeks, but can vary depending on usage and the vapor pressure of the liquid. There is a stainless steel tube that can be seen in this picture, and it extends into the flask, which is where the inlet loop gas is introduced. This loop gas assists in carrying the vapors to the reflux zone and throughout the system. The metal region located above the flask is part of the reflux zone. How is the vapor generated, and what are the functions of some of the other components? The vapor generator has 3 zones, 2 of which can be controlled by the user. There is an inlet loop gas and an outlet gas path above the reflux zone. This allows flow of an inert gas through the generator, and it allows the movement of vapors generated to get carried throughout the system. The first zone, located at the bottom here, consists of a flask mantle. This mantle envelops the flask after it is installed. This zone is crucial for heating the liquid and keeping it at elevated temperatures. This zone is typically recommended to be 5 degrees to 10 degrees Celsius higher than the coldest zone in the vapor generator. It produces vapors in excess. The next zone is the reflux zone. Here would lie the coldest region in the vapor generator, which allows excess vapors to condense and equilibrate to a vapor pressure that is a function of temperature. The control of the vapor pressure is extremely important, as we rely on this to calculate our concentrations in the final blended mixtures. Because of the importance of temperature control here, the reflux zone also has a fan mounted on it for cooling, in addition to heaters. The last zone is the vapor flow zone, and it is not user specified. It is by default set to be 10 degrees greater than the reflux zone, and this prevents vapors from recondensing as it makes its way to the valve. This zone also has a check valve mounted as a safety feature, in case excess pressure is built up in the vapor generator. How do we determine the vapor pressure or concentrations? The vapor pressure of a given liquid is a function of temperature. Antoine equations or high-resolution fluid properties can be used in the system to correlate between temperatures to vapor pressure. The temperature used to determine the vapor pressure is set by the CODIS zone, which is monitored in the reflux zone. In past instruments, vapors can be introduced via pulses. The method of pulse injections are based on filling a loop, as shown in the right, and actuating a rotary valve for vapors in the loop to be carried into the system. Loops can be changed to larger volumes, and the loops shown here are 0.5 cc, 1 cc, and a 5 cc loop. The amount injected are determined by the physical loop size, the concentration of the vapor carried in the stream, and the temperature that the loop is held at. Here is a demo schematic that shows how vapor loop injections are performed. There are 3 gas pathways actively flowing. In this example, helium flows through a carrier and a reference path. The reference path goes unaltered to a reference filament, as shown here. The carrier path goes through the sample and then through the analysis filament. A loop gas here is also specified, and it goes through the vapor generator and carries with it vapors to be filled in the loop. There is a continuous flow during the loop filling process. When the pneumatic loop rotary valve is actuated, the vapors in the loop is introduced and now carried by the helium in the carrier stream. This will make its way to the sample and finally to the analysis filament. If there was a change to the thermal conductivity of the analysis filament due to the injection, the TCD will also have a change in signal. The new feature of the vapor generator in the Autochem 3 now allows a continuous flow of vapors. A heated pathway was added, which we called the vapor flow zone previously. It allows the generated vapor to flow to the vapor valve without recondensing. From the vapor valve, it can be blended into the carrier stream continuously through the blend valve. Because it is a continuous flow, the vapor generated needs to be considered in the mass balance. Loop and carrier flows are determined and monitored by the user specifications and the mass flow controllers. The vapor flow is calculated by using the vapor pressures calculated from the reflux temperatures and pressures monitored internally by the instrument. The final vapor concentration of the blend is calculated by taking the vapor flow over the total flow. Here is a schematic that shows vapor flow being introduced in the system. The reference and carrier gas stream has the same function as mentioned previously for pulse injections. The loop gas stream also carries the vapor as before, but it is now blended into the carrier stream via the blend valve instead of filling the loop. The carrier and loop stream is combined before it is introduced, and the user has the option to bypass or send this through the sample before it hits the TCD. Vapor pulse calibrations can easily be performed before and after an experiment. An empty sample tube needs to be installed prior to performing the vapor pulse calibration. Specifications for the calibration is simple. An inert gas is used. The selection of gas should ideally be very different in thermal conductivity than the active gas. For water, helium is selected because it has a thermal conductivity much drastically different than water. This would increase the sensitivity of the measurement. A flow rate is specified. Keep in mind that the inert gas flow should ideally match the experiment. The flow rate in the loop would allow the loop to be filled. For larger loops and more difficult adsorptors, a faster flow rate can be used. The vapor is selected to calculate vapor pressure and concentrations. The reflux temperature and its range is specified. Typically, it should not be set near the boiling point of the liquid and should be 5 to 10 degrees Celsius cooler than the flask temperature. The valve temperature is vapor specific, It should be set to a temperature higher than the vapor generator. This temperature would also affect how much vapor can be held in the loop. The number of steps determine how many points would be taken specified in this range. Triggering of an auxiliary instrument, such as a mass spec, can be clicked here at the Set External trigger. Here's an example of the vapor pulse calibration. The left y-axis is the TCD signal, and the right axis is the reflux temperature. The individual peaks are integrated, and a peak area versus quantity is automatically generated when a calibration is created. A polynomial fit can be specified. For our use in later experiments, a linear fit including the origin is used. The origin is a point where it specifies 0 quantities for a peak area of 0. A linear fit is selected. As we will see in our TPD experiments, quantities of vapor that lie well beyond the calibration range will be problematic. When extrapolating, we recommend using a linear fit. Higher order polynomials tend to be more erroneous when data is extrapolated far from the calibration window. The vapor flow calibrations have similar user specifications. The difference is that the calibration can be performed before, during, or after the experiment. The calibration uses the blend pathway but bypasses the sample tube, unlike vapor pulse calibrations. Here is an example of a vapor flow calibration. Note that although 6 steps are specified, there are 7 points collected. The first point is a 0 vapor flow. This is accomplished by bypassing the vapor generator to get a baseline value when no vapor was introduced. Notice that the X and Y axes are also different. We are fitting a vapor concentration versus the TCD signal, while with the vapor pulse calibration, it was the peak quantity versus peak area. Here, a second order fit was used. In our example later, the quantities given off during the experiment would lie within this calibration curve. For results that are being quantified and lies within the calibration window, a second order fit is recommended. The calibration of signal is not always required, but it is useful for quantitative comparisons or if those determinations is needed. An example of using this calibration with a real sample can be done by using calcium oxalate monohydrate. The decomposition or the desorption of calcium oxalate monohydrate typically is summarized in 3 steps. First, water is removed, and this occurs first. Second, calcium oxalate then is decomposed to calcium carbonate and carbon monoxide. It is a proportional reaction between the CO. We also give signals for CO2. It is often that mass to charge ratios of 44 for CO2 can also be observed during the second step. The last decomposition step is the decomposition of calcium carbonate to CO2. The graph on the right shows the temperatures, and clearly the first 3 steps for calcium oxalate monohydrate can be seen. It also has an overlay of mass spec data to show the specific species detected. The TCD in blue shows the respective events. The first peak and its quantitative evaluation will be used in this test case. The mass loss in the first step can be determined by comparing the mass of water to the total mass of calcium oxalate monohydrate. It is expected that about 12.33% would be removed. This value converted to quantities of water as a water vapor is 153.16 centimeter cubes per gram of material. The analysis conditions are quite simple for this test case. It is even made more simple and intuitive for users by having a graphic representation of the system when a change is made in the instrument settings. For example, this is the user interface if step 1.02 was to be specified. The system started from an idle state shown in the gray upper schematic. Then the highlighted changes shown in the bottom schematic shows what the user has changed or programmed in the current step. For example, helium was selected as the carrier gas flowing at 50 SCCM, and the detector was enabled. The corresponding changes from the idle state shows the yellow highlight of the new specifications. Users can quickly look at the schematic for a visual check, if this was what they intended to program. This type of interface is also great if a user needs to go back and quickly check their analysis conditions. The sample is then ramped to ADC under helium flow. A period of wait time is used to stabilize the TCD signal and temperatures. Once recording starts, a wait period is used to observe the baseline, then followed by a temperature ramp to 200 C at a ramp rate of 5 C per minute. This is a graph of the TCD signal versus temperature from the previous program. We're using about 60 milligrams, and at these conditions specified previously, the peak temperature lies at around 150 C. The baseline can be observed to return well, and it is well separated from the decomposition step in step 2. This allows us to quantify the water desorption without any interference. As mentioned in past webinars, peak temperatures and shape can be affected by the parameters used in the experiment. For the Autochem version 1.01, a template for this analysis condition is included. The duration of this test from start to finish was about 1 hour. An overlay of the calcium oxalate monohydrate TPD with the vapor flow calibration is shown here. The blue signal is the experimental TCD, and the black plateaus are the TCD signals at different reflux temperatures during a vapor flow calibration. Both datasets are zeroed for easier comparisons. This is to show that the experimental data will be interpolated from the vapor flow calibration, and it is within the first 4 calibration points. If we apply the vapor flow calibrations, the y-axis on the graph would change. The y-axis is changed from a TCD signal to an active gas flow rate in centimeters cubed per gram STP. Although the graph shown here represents the x-axis as temperature, for integration, it would use the time axis for quantification. After the calibration is applied, the peak is selected from the starting baseline to the end baseline. This would be the peak area being selected for integration. The value boxed in red shows the integrated value of 153.38 centimeter cubes per gram, which is very close to our calculated value of 153.16 centimeter cube per gram for water loss. Another example is using the vapor pulse calibration for quantification, an overlay of the experimental water desorption versus the loop injections with the vapor pulse calibration data. It is evident that the experimental values are much larger in comparison to the vapor pulses. This means that the experimental quantification is extrapolated well beyond the window of the calibration data. For extreme extrapolation of data, it is more erroneous, but if necessary, a linear fit would typically give a better value. If we apply the calibration for vapor pulse, notice that the y-axis remains unchanged. A comparison of the peak area to peak quantities would be performed to calculate this value. Here we see an overestimation of the water expected to desorb when applying the pulse calibration data. If we take a closer look at the comparison between the pulse calibration to the experimental data, we see why the values reported has more error. The graph is a peak quantity versus peak area graph, similar to how pulse calibration data is fitted. The points clustered together, the yellow and the gray, at the far left and bottom corner of this graph are the vapor pulse calibration points we use. The point on the far right and top in blue is the experimental data. Comparing the values, the experimental data is over 2 orders of magnitude than the calibration. This far of an extrapolation, while only being 7% away from the expected value, is quite spectacular, even when using the pulse calibration data. The analysis shown previously is a great demonstration of quantification using vapor flow calibrations. We repeated the test with a few more instruments and operators. The preliminary testing shows similar values reported earlier. There was a low of 150.46 with the flow data set and a high of 160.8. but most analyses were on average close to the calculated value. The vapor post-cal had a high of 164.92 and a low of 155.58, and on average 4% higher than the calculated values. Overall, the reproducibility of this method is good, and the flow calibrations applied show it can be used for quantification quite accurately. The next case study is using the calibration data and quantifying sorption or uptake of a zeolite such as ZSM5. ZSM5 and acid site characterization was shown in a previous webinar. With increasing silica to alumina ratio, it was observed that the number of active sites decreased. With water adsorption, there is a similar trend. There is a decrease in water uptake as the silica to alumina ratio increases. Quantifying adsorption or desorption is a bit more challenging. The desorption for calcium oxalate was simpler. Water removal occurs at a higher temperature due to the monohydrate, so a baseline can be established and the onset of desorption can be easily distinguished. For uptake with adsorption and desorption, the time for the active gas to move through the system or out of the system needs to be considered. This is because as soon as the composition of the mixture changes, there is a dead time that is dependent in addition to the properties of the probe, as well as the influences due to the packing of the sample bed and its movement through the system. To eliminate some of these errors, a blank is used to compare signal and a real-time reference when a vapor blend is being introduced. A blank is a sample tube with quartz wool packed, but without sample loaded. A sample analysis is performed right after the sample is located in the same quartz bed. An alternative is using a tracer gas to show the synchronization of the dilution time when the blend is introduced. However, this requires the use of an auxiliary device such as a mass spec to separate and identify the tracer. Utilization of a blank will allow the TCD usage, and it won't require a mass spec. Here is an example of a blank analysis with quartz wool. The conditions for pre-treatment of this is under helium flow. The temperatures used for the blank could be reduced, but this was adapted from the zeolite samples following the blank analysis. The vapor concentrations are created by a blend of 50 SCCM helium in the carrier and 25 SCCM in the loop, with a reflux temperature of 30 C and a flash temperature of 35 C. From a full-scale axis, it appears that the introduction of the blend going from a dry to a wet condition was very rapid. But at a closer inspection, such as the graph zoomed in the lower left, the movement of water can take more than 30 seconds to reach its peak concentration from a dry flow to a wet flow with a blank sample tube. At the lower right-hand graph, we see a similar behavior going from a wet flow to a dry flow. This comparison in a real system using a blank is important, as assumptions regarding the concentrations at the adsorption steps can be better accounted for. Overlaid is the TCD signal including the sample. This is a zeolite with a silica to alumina ratio of 55:1. The relative humidity in this test is about 46%. The sample is the blue curve and the blank is the orange curve, or the curve that has a rapid increase from dry to wet conditions and from wet to dry conditions. For the sample, when going from a dry to a wet condition, there is a delay in the TCD response when comparing to the blank. This is expected for adsorption. The delayed signal is due to the adsorption of the vapor onto the sample. The TCD will increase and gets closer and closer to the values of the blank once the sample is saturated. We see the sample reaches its peak around 60 minutes. The wet to dry curve allows comparisons for desorption. The blank sample reaches a dry state rapidly. The sample shows a delay as well due to the desorption of the vapors. However, note here, the desorption curve takes a considerable amount of time before it reaches the baseline, seen on the blank. To perform the quantification, the differences between the blank and sample is compared. Adsorption would be taking the difference going from a dry to wet conditions. Desorption would be taking the difference going from a wet to dry condition. The grayish curve shows the difference between the blank and sample for dry to wet conditions. This would be the volume for adsorption. Integration of the adsorption and normalizing it to the dry sample mass allows us to report the quantity of water vapor adsorbed per gram of material. The values reported here was truncated, and the adsorption and desorption both were given 40 minutes for comparison. The desorption quantity is shown in yellow. The desorption value is similar to the adsorption. You can also see that the desorption curve needed a longer time to fully dry. For materials such as this, drying may be much more difficult at ambient temperatures. The previous data shows integration up to 40 minutes. Here, the adsorption and desorption windows were extended even further. Comparing to the 40-minute window and the 90-minute window, the adsorption values were quite similar. When extending the desorption, the quantities desorbed appeared to increase quite drastically, especially if the time was extended. The integration and comparative method here has some limitations. Cumulative errors may be problematic, and for samples that have a slow uptake or slow desorption, it can be significant if the times are significantly extended. The calcium oxalate monohydrate test case had a theoretical value for comparisons. In this test case, we compare the quantities reported to values measured by other techniques. The first technique is a dynamic flow, but the gravimetric method. The instrument used for this technique also generates and blends to a specific RH. The limitations of this technique is that the speed from in situ drying to analysis can be longer, and the temperatures for in situ is limited to 200 C. The data here has a sample degas in situ and only to 200 Cs for several hours, then undergo a helium dry flow at 200 SCCM for 720 minutes before introducing the humidity. The values reported will be a % weight loss or gain depending on the analysis conditions. The isotherm collected from the gravimetric method is represented in blue. The next method is also dynamic, but monitoring the effluent gas with a TCD on the Autochem 3. We use a single point at roughly around 46% relative humidity for demonstration. The degas was performed in situ up to 350 C, and in a window of less than an hour is required to cool to 25 C and began the adsorption study. Keep in mind, the temperature range for this furnace could go up to 1200 C. The last method for comparison is a static method on our 3-flex instrument. For static measurements, the sample is not under flow, but uses a dose and weight method. The sample was dried externally and followed by an in situ degas on our instrument at 350 C for 4 hours under vacuum prior to adsorption. The advantage in this method is that the sample can start at a very dry state, and the impact of moisture due to a carrier gas is avoided. The vapors introduced could also undergo in situ freeze-thaw purifications. The higher values reported here may be impacted by starting the sample at a drier state. The Autochem methods are comparable to the static values, and this may be an outcome of how dry the sample is prior to the measurement. Here's a comparison with the single point adsorption of other CSM5 silica to alumina ratios. The 3 points from left to right are a silica to alumina ratio of 30, 55, and 280. Low silica alumina ratios has the highest uptake, and the highest silica alumina ratios had the lowest uptake. The relative humidity used for all 3 comparisons was at 46% RH. The analysis temperature, like before, was set at 25 C. The static measurements shown for comparison are taken from our 3-flex instrument. Please note that the comparisons throughout this webinar for each measurement, a different aliquot from the sample that was being sampled. The use of blanks shows great results, but the extra analysis and data reduction will require a bit more effort and time. A faster measurement could be performed without a use of blanks, if a zero state driven by temperature could be assumed. In this example, the zero, or the dry state, under any humid flow is specified to be 350 C. It is assumed at this elevated temperature, the zeolite does not significantly absorb moisture, even if it is present and continuously flown over the sample. For materials and samples, this assumption needs careful consideration. Does a sample absorb at this elevated temperature? Can it withstand this elevated temperature? Does this environment, such as steaming the material, would it change the material? The instrument is capable of performing this measurement with ease. The analysis starts off with a wet flow with a sample at elevated temperatures, 350 C. A short baseline time or measurement is being taken, and then the sample is reduced to 25 C to measure the uptake. The temperature ramp was set at 10 C per minute and shows great control to 25 C. Integrating this adsorption, we get comparable results as used in the blank comparison. Shown here is a 16-step isotherm created by blending in the Autochem of the ZSM5 sample with the silica of alumina ratio of 55. The temperature overlay in green contains all the temperature overlay of each measurement. This shows great temperature control and reproducibility. A vapor flow calibration was applied so that now the y-axis representation shows the appropriate active gas flow rates of the diluted blends. Each point takes about 80 minutes to measure. However, additional time to degas between measurements was needed. This time can be shortened and optimized. Some optimization parameters would be sample mass, temperature ramps, degas temperature and hold times, total flow rates, and vapor generator zone temperatures. This is our first attempt here, and it shows very promising results. A calculated RH was assigned to each point, and the quantities of water absorbed was tabulated from the fast type of measurements. These values are overlaid and labeled as TCD flow in yellow in the isotherms, and it's compared to the gravimetric and static method shown previously. Once again, here we see agreement of the isotherm in the Autochem 3 to the static measurements on all three flex. The curve and the quantification can be improved, but still it is a pretty decent isotherm for a first attempt without any optimization. In summary, we introduced the vapor generator and an overview of how it works in both pulse and flow, the calibration user interface and results, as well as a few best practices regarding fits with the test cases we use today. The calibration is automated with user specifications that are well adapted to different type of vapors. Calcium oxalate monohydrate is a great material to demonstrate the quantification and the system's performance as a whole. Values are very agreeable with theoretical calculations with a number of operators and instruments in different environments for demonstration. Next, we looked at ZSM5 with varying silica to alumina ratios, and we looked at the water uptake for adsorption and desorption. We obtained better values with the adsorption due to the more rapid uptake and calibration. We looked at a blank method using elution time and signal comparisons to a blank, and it shows agreement to static values for the adsorption and just slightly higher than the gravimetric method. There is a possibility that the activation or purity of the carrier flow may be an impact in comparison of the gravimetric with the TCD or the static method. A fast measurement using a temperature ramp from a high temperature to a low temperature without using a blank was also demonstrated, along with the isotherm using this method. Similarly, the isotherm was in agreement with the static measurements. Finally, when comparing the uptake of the silica to alumina ratios, we find that as silica to alumina ratio increase, water uptake decreases. This definitely was an exciting study and only looked at one of the few applications of vapor flow. Here we find that activation with rapid temperature control really work well in our favor. We are excited to see other uses of this feature and use it in more creative ways. Thank you for your attention, and we really appreciate your time.